Okay, now there's a little section in the AQA syllabus and it says using moles to balance an equation. And what you've got to do here really is the reverse of a reacting mass calculation. And in that case, you're given the balanced equation and you have to work out, predict what mass of stuff you're going to make and what mass of stuff you'll use up. In this one, you're given the masses and you have to work backwards to work out what the correct equation is. So what, as an example here, is making iron chloride. Now, iron chloride, there's two different iron chlorides. There's iron 2 chloride, FeCl2, and there's iron 3 chloride, which has got the formula FeCl3. And we can make this in the lab, iron chloride. So what you're going to have a stream of chlorine gas coming in here into this tube. And here we've got our iron metal, some iron filings probably, and you're going to heat it up really strongly. What happens, it reacts with the chlorine, and the iron chloride that will be made in this tube, and this is a gas, all right? It's quite volatile, and it will pass through this tube here, and then this is a cold flask. It will condense. It was actually sublimes. It will turn into a solid on the surface of the flask here, and any waste gases, the waste chlorine gas, because that's in excess, will come out there. So you'd have to do it in a fume cupboard. So this is the iron chloride, and we want to find out what kind of iron chloride it is. Is it iron 2 or iron 3? So when we do the experiment, you can find you weigh out, make the following weighing, okay? 1, the mass of the iron that you start with, and 2, the mass of the iron chloride that you make. Now the way you do that is you get this flask here, you weigh it at the start, and then you weigh it at the end, and of course it's going to be heavier because it's got iron chloride in it, and then you subtract to find the mass of the iron chloride. Okay, so we've got two possible equations there. We don't know which one is correct. Okay, so the two possibilities are, we could have Fe plus Cl2 goes to FeCl2, iron 2 chloride. That equation is balanced. We don't need to do anything there. Or the alternative is you made iron 3 chloride with Fe plus Cl2 goes to FeCl3. So the only way we can balance that is by putting a 3 there and put a 2 in front of the iron, and we obviously need a 2 there. So we've got to find out which equation is the correct one. Is it equation 1 or is it equation 2? So which iron chloride are we actually making? So how do you go about that then? Right, so what we're going to do is we're going to find out the moles of iron. Okay, and the way to find out the moles of iron, well, we know the mass, so we're going to use this equation. Moles equal to mass over mR. Atomic mass of iron is 56. So moles iron that's going to be equal to the mass, which is, we need some figures here, don't we? Right, so here's before we start, let's write down the results of the experiment. So start mass of iron that's equal to 3.42 grams. That was 3.42 grams. The mass of iron chloride made that's going to be more than that, and that was actually 9.92 grams. Now, it's probably pretty useful here to work out the mass of the chlorine in that has reacted. So, and that is going to be simply the difference between these two masses. There's the iron, There's the iron chloride. So 9.92 minus 3.42 is the mass of the chlorine. So let's do that. The mass of chlorine reacted is equal to 9.92 minus 3.42, and that is equal to 6.5 grams. 6.50 grams. Okay, I'm going to copy those equations because we need those for later on. Okay, so I'll put that down there for in a minute. Right. Okay, so now let's work out our moles of iron, shall we? So moles of iron, that's equal to the mass of iron divided by the MR, well really should be the AR because it's the atomic mass for iron. Atomic mass for iron is 56. Okay, so the number of moles of iron is going to be equal to 3.42 over 56, which is equal to 0.061. Right, now we're going to work out the mass of chlorine. I'll put that bit later on there. So the moles of chlorine, sorry. So let's work out our moles of chlorine. Moles of chlorine. Moles of Cl2. Well, the AR of the atomic mass of chlorine is 35.5. So chlorine Cl2 is going to be double that. So that's equal to the mass over, because it's Cl2, 35.5 times 2, 71. So the mass of chlorine we worked out earlier was 6.5 grams over 71. That is equal to 0.091 moles. Okay, so we've got our moles of iron here, and we've got our moles of chlorine there. So let's see which one of these equations it will fit. Okay, so right, let's do the moles Fe. I've got moles to the moles of chlorine. Well, moles of Fe is 0.061 and this is 0.091. Now to simplify this ratio, I'm going to divide by the smallest number. So that is going to be 0.61 divided by itself because that's the smallest number. And that's 0.091 divided by 0.061. If you do that, you get a 1 to 1.5 ratio. 1.5, not 5, sorry. And so I can just double that to get a 2 to 3 ratio. Now, which one of these equations does it fit in? Well, this equation here, if you have 1 mole of iron, you have 1 mole of chlorine, and we're not getting that, so that equation is wrong. This one here, you get 2 moles of iron to 3 moles of chlorine, so this is the right equation. So in this experiment, we've actually formed iron 3 chloride. We haven't formed iron 2 chloride. So that's one way, one example of using moles to work out the balanced equation. You get the masses, you work backwards to get the equation. Right, here's another example now, and it's right here. So what here is we are going to find out, this little piece of apparatus is to find out the well, you're going to react copper oxide. So what you get is you get copper oxide, which is in here. So copper oxide, and you react that with hydrogen. So you pass a stream of hydrogen here, H2 gas here, and you actually light it there, and you burn off the excess hydrogen, little flame, because you don't want the hydrogen just escaping into the room. It would be dangerous. Okay, and you're going to form copper, metal, and water. Now, we're trying to find out the equation here because there are actually two versions of copper oxide. It's a transition metal, a bit like iron is a transition metal. Forms two different ions, two different valencies, if you like. So there's two kind of copper oxide. There's copper 1 oxide, which has got that formula, and there's copper 2 oxide, which has got that formula. So let's write down the two possible equations we could have there then. If it's copper 2 oxide, the equation would be Cu2O plus hydrogen gas goes to two copper atoms, 2 coppers and 1 H2O. If on the other hand it's copper 2 oxide, then you're going to CuO plus hydrogen. That will give you copper, 1 copper that time. Okay, so we're going to find out which of those equations is right. And tell us equation 1, equation 2, and tell us which one is which. Okay, so the experiment, what you do is, I'll copy this again because I'll probably need it later. Okay, so in the experiment what you do is you weigh your copper oxide at the start, so mass of copper oxide, and then you weigh it at the end when it's being reduced. You remove the oxygen and it's being reduced to copper. So you have to weigh the tube first, put in your copper oxide, find out the mass of copper oxide by subtraction, then weigh the tube at the end of the experiment, subtract the mass of the empty tube, and that will give you the mass of copper metal. Okay, so we did this experiment, and on this occasion we added 1.85 grams of copper oxide, and we ended up with 1.48 grams of copper. Okay, so we can't work out the moles of copper oxide. That's because we can't do that, because moles is equal to mass over mR, but we don't know what the mR of the copper oxide is because we don't know which one it is, whether it's copper 2 or copper 1 oxide. But we can work out the moles of copper. Okay, so let's do that. Moles of copper, mass over mR, which is AR really for copper, which is 64. So that's going to be equal to 1.48 divided by 64. That will give us 0.023 moles. Now, we can't do anything with the copper oxide, but what we can do here, we know from the equation that this gets the mass of oxygen which is reacted, because we can subtract the mass of the copper formed from the mass of copper oxide, and that should give us the mass of oxygen reacted. So let's do that. So mass of oxygen reacted, so oxygen atoms, is equal to the mass of the copper oxide, 1.85, minus 1.48, and that is going to give us, that gives us 0.37 grams. Now look, for every mole of oxygen, we're going to make 1 mole of water. Okay, so let's work out the moles of oxygen atoms, and that will give us the moles of water produced. Okay, so moles of oxygen atoms, not oxygen O2, so is equal to mass over the AR of oxygen, which is 16. That's equal to 0.37 over 16, and that is equal to 0.023. Now, the moles of oxygen is 0.023, so that tells us that's the same as the moles of water produced. So let's write that down. Write it down here. Moles of H2O made is equal to 0.023. Now we're going to see, so we know the moles of copper and we know the moles of water in that equation. That should be enough to tell us which is the correct version of the equation. So let's just paste in those equations there and see which it should be. Okay, now if it's equation 1, we should get 2 moles of copper should give us 1 mole of water. Now that's not what's happening there, because look, the same number of moles, 0.023 moles of copper gives us 0.023 moles of water. So you get 1 mole of copper gives 1 mole of water. So it's not that equation, that's wrong. So let's just check if it's equation 2. It should be, yes it is, because look, for every 1 mole of copper, you should get 1 mole of water, and we do get that. So that is the correct equation, and that means we must have started off with copper 2 oxide and not copper 1 oxide.